Okay, so today I just want to review mathematics for machine learning. Yeah, this is a pretty common one, it seems, going on around as recommendations. So I do have a few comments. First, I just want to comment on, I do have screenshots of the reading that I had done here, just to kind of say, so they're probably what your textbook should look like. And I do think it's kind of instructive to see that other people take many, many notes because reading can take a lot of time. And if you're not spending a lot of time with a book, it's perhaps not even really worth reading. Um, Now, one kind of caveat to that is, for example, here I have goals based portfolio theory from Franklin Parker, which I thought was actually quite an interesting book. But I'm already familiar with many of the topics because of my involvement with the CFA curriculum. So, just naturally not many notes to take. But, anyways, we can see that these are still marked up. But, whenever I'm learning something new, one, it will take a long time. And uh, at least if you actually want to understand and be able to answer the questions, like I'll go over in a minute. Um, Takes a long time, and your pages should probably get marked up like this. And I do largely suspect that most people that recommend and review books online, as I've noted with, say, Rich Dad, Poor Dad, don't actually read the books that they discuss, which I think is a big problem because that can lead to a great deal of time wasted, I feel. And also, just people buying books that just sit on shelves. You should write on them, and don't trust anyone if they don't have writing on their books. So there's that. Now, just some comments to make on the book. For some pros, it goes over a lot of theoretical math at the outset, including some introductions to group theory, for example, as you can see here, which I think is good. A lot of people don't think that theory is important, but I would say that's kind of silly. Um, I think that's is pretty important, especially when you start to realize that we're in an age of arguably an absurd amount of information available to us. You need that theory to do two things: one, sift through what makes and does not make sense, and the other is if you want to reconstruct or create new things, then you will find yourself needing theory, at least if you want to have direction while you're doing so. Um, if you want to kind of do that like aimlessly for some reason, I suppose you can do that. Good luck. But otherwise, you'll need theory. So there's that. And math is one of those topics that's like that. It's a lot easier to remember how to get to an equation than it is to remember all of the equations in physics per se. And machine learning is obviously a lot of equations as well. Okay. And another nice thing actually about all of this is there are lots of proofs in the later chapters, especially, and all of those proofs seem very natural and intuitive, based on the material here and the way that those variables get manipulated, right? So yeah. Generally, the explanations are good, and it's generally self-contained. So those are all pros. Now, some cons, kind of directly related to some of those pros. For example, there are some issues with self-containment. For example, in the topic of infimums and supremums, which I don't believe are covered in a high school curriculum, but I'm not sure. So that they don't find that seemed a little bit odd. And some of the notation also has some issues. With not being fully explained, although you can go and find the explanation, so it's not necessarily an issue. The audience doesn't seem to be correctly defined. I would say, especially at the outset. I mean, although you do certainly need calculus, I think, to understand the book, you probably do want a little bit more than high school math. Otherwise, I imagine this is going to be incredibly laborious, at least if you're trying to answer the questions. If you're just trying to read this, I'm sure it'll, make sense. But just to give you an example, right? The second chapter, which is where the math sort of starts, opens up basically with like sets and group theories. So here I have a shot of groups because this one ties directly into the question set that I have here. So basically, to just kind of explain this, right? The very first question, opening chapter 2, starts out with basically, okay, we have some set, real space excluding -1 with some operator, and then this is how the operator is defined, and then we want to show this in a abelian group, right? So how do we do that? Well, we go back to our definitions, which we know to do that if we've ever done this before. But you go over all of your definitions for all x, y in this set. X operating on y is also part of that set, right? For the closure property, and show that this is true for that operator. And then we've proven the closure property, for example, right? So we go through the list of properties and definitions, or elements of the definition of the abelian group down here, and if it has all those properties, then it is an abelian group, right? Okay. Now, obviously, you don't do any of that in high school, though, so that and probably not even anything like that, to be honest. Yeah, so stuff like this is very difficult to get over, and then also even some of the stuff on for example the Taylor series and the gradients, right? Probably not too much of a stretch actually to understand if you do just have high school calculus, but it's still easier if you do have some familiarity with multivariable calculus to quickly understand the concept of the gradient, as it does get applied as a central part of the back propagation algorithms that are discussed in the book. So I'm just going to say, if you have a high school background, that's fine. What I would recommend you do, though, is brush up on your calculus and linear algebra and probably your probability. So there's a number of resources that you can use to do that. I'm told that Thomas's calculus book is great. There are a number of resources in linear algebra, et cetera, right? Another great place to go is if you're already kind of familiar with everything. You can also use the Schaum's books. They're kind of old now, but that was a recommendation I got from somebody else on YouTube. Who suggested Schaum's books, and I thought they were really interesting because they do go through all the concepts very quickly with just lots of questions. So that can be nice as well, but not very detailed. I would say on the theoretical side of things. So there's all that. The second half of the book, another con, does not contain questions. So once you actually get to the machine learning concepts, there aren't questions on, for example, calculate, derive the Bayesian model for the, let's say like chapter 9 for linear regression, right? Develop a probabilistic model to, apply linear regression, something like that. That's actually, like now that I have this up too, actually, you can see that this is kind of about the same topic actually, although different because this is with principal component analysis. The drawback of that is I think that if you don't solve questions on here, it's very difficult to understand how all of these variables relate to each other. I mean, you can kind of understand if you go through the proofs and you understand the proofs, right? You can kind of understand. It's still worthwhile to have questions on that kind of thing and go to answer them, because you recite and you solve things and you really get to look at the relationships between the variables and the equations. So I think that's all worthwhile to have. Okay. So let's make that comment. And then arguably as a sort of last criticism is that there's arguably not enough of a probability theory focus in the first half of the book, given how much of the machine learning concepts rely on probability. And I know there are other resources that can be used, like probabilistic machine learning from, I think, Murphy. But it still seems like maybe there should be more in some segments, just based on its importance. Yeah. Now, here we have another snapshot of the book from the likelihood and joint distribution section from PCA, right? The dim reduction. Maybe just gives you another idea of some of the concepts in the book. These should all be like, I think this is all pretty easy to follow if you've been going through the book, of course. So yeah, but that's just another snapshot of what that looks like, and also again how reading should probably look in the academic setting. Okay, so I think those are all the comments that I had to make. Overall, decent book. I wouldn't say you should spend a tremendous amount of time with it though. And you're almost certainly going to need additional resources aside from this to fully understand what's going on. And also it's probably not enough if you wanted to find the minimum resources to apply to create models, for example. For something like that, I'd probably actually recommend, and although I didn't actually, I opted not to finish the book because I have familiarity on a bunch of the other topics already. But deep learning, math and architectures of deep learning seem to be significantly better than I thought it would be. Also, from a practical side of things, I think that the code is very illustrative of what it would actually look like in a more it has more intimate code than most books, let's put it like that. So for example, if you read something like Python for Machine Learning cookbook, a lot of that is calling objects from modules, which is fine, but it's not really something I would want to read for any reason, to be honest, because you can just look all of that up. Whereas the math and architectures for deep learning does go over a lot more, like how do you represent a Gaussian distribution in Python, for example, from scratch, right? Stuff like that, which I think is much more useful and worth going through. So, okay. So anyways, I think that's the end of this review. Yeah, that's I think all I have to say. All right, I hope that was useful. Bye.